Now let's write a program that generates prime numbers and stores those prime numbers. And the reason why you might want to do something like this would be if, because of the computational effort it takes to find the primes initially, you may wish to save them for later use. Now, we really could write them to a file or whatever, but you wouldn't want every time you need the list of prime numbers to go out and generate them from scratch. So when I'm thinking about all those prime numbers and how I'm going to save them, what comes to mind is an array. So that's why we're having this application. So recall that we did something like this. We said our function was int is prime, int n. And we said that given an integer n, we can determine if it's prime by seeing if any of the integers in the range of 2 to n minus 1 divide evenly into it. If any of those do, then the number's not prime. Otherwise, it is prime. So int I for I is equal to 2, I is less than n, I plus plus. If n mod I has no remainder, then this number can't be a prime number. That is, n can't be prime. So we return 0 here. Otherwise, we make it through the whole sequence of numbers, 2 to n minus 1, without finding anything that divides evenly into n, then the only things that do divide evenly into n are 1 and n themselves. So by definition, n is prime. So we return 1 to indicate that. So remember, this right here is our way of indicating that it's false that n is prime, and this indicates that it's true that n is prime. And let's just check that this works first, and then we'll go back and store the numbers. For I is equal to, let's check the numbers in the range of 2 to 20. I is less than 21. I plus plus. If is prime I, print %d is prime. And we actually had done this. Let's make one little change here. We said we don't actually need to check all the numbers. We just go up to the square root. So we need to equal here. So this was a performance improvement. Don't check all the numbers. Just check as many as it takes to figure it out. Dash lm, .c. And there's our prime numbers in the range of 2 to 20. All right? So now we say we want to store these numbers. So let's write a function to do that. And that function will actually call the is prime function. So that's right. So I'm just going to do this the way I'm going to call it. I'm going to cut and paste some of this code. We'll do this, call it save primes. So it's not returning anything, it's not receiving anything, so both of these are void. And there will be some hard coding in here, but I'm not worried about that right now because we're just trying to demonstrate some things. Right? Sorry, cut that out too soon. So now we say, well, if the number is prime, we're going to save it. And if we're going up to 2 to 20, technically that's 19, but we'll just do this. Int primes, we'll allocate memory for 20 numbers potentially. And then later on, we want to print those values. So I'm going to have a function, and we'll say print primes. and we'll give the array primes. As in this case, I will pass in the values so we could change that if we want to. Let's write that function. Void int primes. Let's just call it p here. Int length of it. And I'm going to put the function here. It doesn't matter about the order of these functions. But I won't be able to see everything else that we're doing later. And let's do this. For I is equal to 0, I is less than length, I plus plus. Print piece of I. And then we'll print a new line at the end. So this will essentially print the numbers across, so they're easier to see. One new line at the end. So now we're not really printing here, we want to save. So the question is, where do we put everything? So let's do initially what I consider the inferior method, and then we'll talk about how to improve it. But it's certainly a conceptually easy method to do this. Say, okay, primes I is equal to I. So if there's no bugs here, let's see what we get. So I got 0, 0, 2, and 3 are primes. I got 194. Where'd that come from? 5. This negative number with a large magnitude, there's a 7 that's a prime. Another negative number with a really large magnitude, 11, 13. What happened here? Well, remember that when I introduced arrays, we said that if I allocate the array in this method, I'm not initializing the values. So we should assume that they're garbage values. And all I did was just overwrite those positions that contained or would eventually correspond to primes. So that meant this 0 is a garbage value. This is a garbage value. There was a garbage value here, but I overrode it with 2. There was a garbage value here, but I overrode it with 3. So that's garbage, that's garbage, that's garbage. So I have all these garbage values in there. So if I wanted to take this approach, and I wouldn't because I consider it inferior, how could I at least try to fix this? Well, I could say that in terms of printing, I just want to print the actual primes, but how do I know which of these are primes? Well, if I'm going through and printing things, what I could do is look for something that can't be a prime. So we know that 1 is not prime by the way primes are defined. We know that 0 can't be prime. We know that negative 23 can't be prime. So what I'm going to do is this. I'm going to initialize all values to zeros. Some of these did stumble into being zeros, but there's no guarantee on that, right? Because I don't know these will always be zeros and this won't, and this will be a 0 and this won't, and so forth. But I'm going to initialize them all to zeros, and then I can come down inside my print primes function and say if p sub I is not equal to 0, then print the number. So now let's see what happens. So I just got rid of these things. I didn't change the array. This is still the array contents or whatever the numbers are now. I don't really know about the garbage values. But what I do know is I allocated memory for 20 integers, and that's how much memory is being used. All I did was change what's being printed. So could we do that? Certainly, I just did it, which proves it. But I consider that inferior. And the reason why has to do with performance. Now what I'm doing is, on every iteration of this loop where I'm printing, I have to ask a question. Is this really something I should print or not? And if this right here is true, then I print. Otherwise I don't. But I still have to ask the question each iteration. So for something small like this, you'll never notice it. But for a program that had an array with, say, millions of numbers or billions or whatever, then I'm taking a performance hit. So I don't really want to do that. So let's look at an alternative way. What if instead I just put all the primes at the beginning of the array, and so I only printed those spots that contain the primes, because I just say stop printing after you run out of primes, essentially. So in this case, I have these 8 numbers, so I only have the loop run 8 times. How would I do that? I have a couple of things to consider here. One scenario would be if I can find some type of mapping that says, given the number to store, what is its index, then I could do that. So for example, if I want to generate these integers from 2 to 20 and only store the even integers, I could find a mapping that allowed me to figure out what the index is of the number being stored. But the problem is with primes, I don't have any such mapping. So instead, what I'm going to do is I'm going to have a separate index for storing numbers that's different from the number to be stored. Right here, I'm trying to take advantage of the fact that I have an index I and I'm using it for 2 different things. The number to store and the index for where to store it in my array. But now I'm going to create a separate index variable. So let's do this. Prime index. And I could either allocate it, or excuse me, initialize it here, or I could actually do it right here if I wanted to. So I've done it here. So now what I'm going to do is change this to prime index. But initially it's going to be 0 when I store the 2, but then I need to increment it so that it's 1 for storing the 3. It should be 2 when I'm storing the 5 and so forth. So I also need to increment it by 1. Now technically I could do it right here, but let's do this instead. To make it more readable. And we do this. So now I'm going to come back down to my printing function and get rid of this statement to see where things are at. So we still have all 20 array positions, which I initialized to 0, although now I don't technically need to, or technically I won't in a moment. We can see these are all the values, so the primes were put at the beginning positions, but now I can do something like this. Instead of printing all 20 positions, prime index will be a count of how many things are stored. So for example, let's say I stored just 2 and 3. Well, initially prime index was 0, so when I stored the 2, prime index went up to 1, and when I stored the 3, prime index went up to 2. So the value of prime index is the same as how many numbers I stored, 2. So now when I do this, now my loop only ran 8 times. So I saved myself some work there as well. Now there is another potential issue here that we don't currently have a way of dealing with at this point in my video lecture series. Right here I had to know in advance how much memory to set aside for potential primes. And obviously this can't exceed the quantity of numbers I'm evaluating. But even though I'm only printing these 8 numbers, I still allocated memory for 20 numbers. So what can we do about that? Because technically I'm wasting space. Well, if you're using this method for creating an array, there's no way of changing this within this function. I've allocated memory for 20 numbers, and whether I use one of the numbers or all 20, there's no way to change the fact I allocated memory for 20. Eventually, we'll know how to allocate memory dynamically, which means technically I can either start with a small amount of memory and grow it as needed, or I could start with a larger amount of memory and shrink it once I realize how much space I need. So what I could do is I could start with this much memory, something to store 20 numbers, and then once I've finished storing numbers in my array, I could shrink it back down to such that I'm only using up space for 8 integers. But we don't know how to do that yet, so that's something to consider later. But I would consider this method to be superior for the reasons I've given.